A standard normal random variable has PDF, where the expected value is 0 and the variance is 1. More conventionally, we say it has mean 0 and standard deviation 1. For reasons that will become clear after a few years of graduate mathematics, the normal distribution is extremely important. Otherwise, trust us, it's important. Full disclosure, unless you take those several years of graduate mathematics, you will never ever need to worry about the exact form of the PDF function. So while it's actually rather interesting why pi shows up in the normal distribution, it's not actually important. And yeah, I know saying that risks having my mathematician card revoked, but the few things that you do need to remember about the normal distribution: the PDF is symmetric about x equals 0, and the PDF is a PDF. The graph of the PDF looks like this, and it gives us a distinct shape usually called the bell curve. Since it is a PDF, we can find the probability that our random variable is in some interval by evaluating an integral. There's just one problem. We can't actually evaluate this integral. Specifically, there's no elementary function whose derivative is this PDF. Well, remember, a problem exists whether or not you can solve it, so how can we use the normal distribution? To do that, we can approximate the value of the integral numerically. Most statistical programs have built-in functions that do this, and there are online calculators that will also compute these values. But what if civilization collapses and the internet and all electronic devices are destroyed by a massive EMP burst, and you need to find the probability that the height of a 3-year-old tree is between 27 and 38 inches without a calculator? What would you do then? We can use numerical methods to find the value of the integral for any limits a and b. But since we don't know in advance what values someone will need, it's easier to compute the value of the CDF, and this produces the standard normal distribution table. Before we introduce the table, let's express some probabilities using the CDF. The key thing to remember is that on the graph of the PDF, probabilities are areas. Since our CDF is defined by the integral of a continuous function, it will also be continuous. This means that including or excluding a single value will not change the probabilities. We're not going to sweat the equality. So let's start off with a few values. Let's find f of 0. So note that our PDF, and this will probably be the last time we ever write this out in full, is symmetric about the mean, which happens to be at x equals 0. The probability that z is less than or equal to 0 will be the area to the left. By the symmetry, this is half the total area. But since the PDF is a PDF, the total area must also be 1. And so f of 0 is half 0.5. So let's express the probabilities in terms of the CDF of the standard normal distribution. So remember, the CDF gives the probability that our random variable is less than or equal to a certain amount. So if that's what we're looking for, the CDF gives us the value. Now, while we could simply remember that the probability x less than or equal to something is the CDF, it's useful to keep in mind the area is the probability. And so for things like the probability z is less than or equal to 2, we want the area to the left of z equals 2 on the graph, and likewise for the probability that z is less than or equal to 1. How about the others? In general, to do problems like this in the hardest way possible, don't draw a picture. While this may give you street cred among gangs of rogue mathematicians, why would you want that? Draw the picture. So, if we want the probability that z is greater than 2, we want the area to the right of z equals 2. Since the CDF gives us the less than areas, then the area to the left will be f of 2. And since the CDF is a CDF, then the area under the entire graph must be 1. And so the area we want must be 1 minus f of 2. Similarly, the probability z is greater than -1 will be the area to the right of z equals -1. But the area to the left will be f of -1. So the area to the right will be 1 minus f of -1. Finally, this probability will be the area between z equals -1 and z equals 2. We can view this as the area to the left of z equals 2, which is f of 2, from which we'll remove the area to the left of z equals -1, which is f of -1. And so this probability is the difference between those two CDF values. So, suppose x has a standard normal distribution and the CDF has values. Let's find this probability. Since we want to do this in the hardest way possible, we won't draw a graph. Wait, what? Let's draw a graph. The probability corresponds to the area between z equals 1 and z equals 2. So this area will be the area to the left of z equals 2, that's our value f of 2.98, from which we'll remove the area to the left of z equals 1, which is f of 1.84. And so that probability will be